Welcome back, everybody. In this section, we're going to combine a few of the ideas that we've built so far and develop the idea of a logarithm. And so what we want to be able to do by the time we're done with this lesson is you're going to know what a logarithm is. You're going to be able to write logarithmic expressions as exponentials and back again. You'll be able to evaluate logarithms. You'll know what the graph of a logarithm looks like, and then we're going to solve some simple applications where we need logarithms. So here we go. Before we start the lesson, I want to do just a little review with you and show you kind of where we're headed. I'm going to give you a really easy equation to solve. Suppose I asked you to solve the equation 11 is equal to x squared. Now that's a piece of cake. You know how to solve this. If 11 is equal to x squared, we'd take the square to both sides and conclude that plus or minus the square root of 11 is equal to the square root of x squared. And getting rid of that square root gets x by itself, and x is equal to plus or minus the square root of 11. That's easy. Now, I'm going to change that slightly. Let's switch the 2 and the x. Let's say that 11 is equal to 2 to the x power. Now, if I ask you to solve that, what would you do? Well, that's a little bit tougher. It's tempting to say that we will take some root of that, but we don't even know what root we would take. Here we took the squared root because it was squared. We don't know if that's a cube or a second root, or so we can't really use a root. And that is the problem. This is a tough equation to solve. Now, you can estimate this. We know that 2 to the third power is equal to 8. So our value of x has got to be a little bit more than 3, because 2 to the third would only give us 8. We need to get to 11. But we also know that 2 to the fourth is equal to 16. So an exponent of 3 would give us 8. An exponent of 4 would give us 16. But we need to come up with 11. So it's got to be somewhere in between there. So we know that our value of x here has got to be less than 4, but bigger than 3. Our solution has got to be somewhere between 3 and 4. But that's the best we can do. This type of problem is solved really easily if we introduce the idea of a logarithm. So let's see how that works. So let me ask you this. From the work that we've done before, are exponential functions one-to-one? Well, let's think about that for a minute. Let's take a simple exponential function like f of x is equal to 1 times 2 to the x power. We just got done graphing those in a previous lesson. You know that this function will have an a value of 1 and a b value of 2. Since b is equal to 2, this will be exponential growth. And therefore it'll look something like that. So the question is this function going to be one-to-one? Do you remember how you tell? Yeah, it'll be one-to-one. Why? Well, because it passes the horizontal line test. This function would only intersect any horizontal line one time, and since a horizontal line will only hit one time, it passes the horizontal line test, and therefore, yeah, it is one-to-one. And if it's one-to-one, will it have an inverse? Well, yeah, because one-to-one functions have inverses. So then the question is, well, how do we find the inverse of an exponential function? Well, our three-step process won't work, and so we have to define what a logarithm is. This is the most important fact of this section right here. This is something that you should write down on your note sheet in preparation for the final exam. The definition of the logarithm, which is right here, is what we're going to do all of our work based on for the next few lessons, actually. So, if we know that x and y are related, but y is in the exponent, then we can say that that y value is the log base b of x. Now, that's confusing, but I want you to recognize a couple things, and then we're going to put this into action. Every logarithmic statement has 3 parts, and every exponential statement has 3 parts. And as it turns out, they each have a role. First of all, the base in the exponential statement b, just like we saw a minute ago where b was 2, that base in the exponential statement becomes the base in the logarithm. We would say that that is log with a base of b. The exponent, our y value here, that becomes the isolated variable over here. And that's going to lead us to this fact right here. A logarithmic value is always going to be an exponent. That is to say, anytime you try and figure out the value of a logarithm, you are figuring out an unknown exponent. And x, which is what we call the argument of the logarithm, that is what the exponential value is equal to. So, this fact we're going to use a lot. If x equals b to the y, then y is equal to log base b of x. Those same three parts, x, y, and b, are true in both statements. Let's look at some examples and make that start to make some sense. Okay, now there's no work to do. There's no solving in these three statements. All we want to do is change their form. We want to write each logarithm as an exponential equation. And here again, we're going to use this fact. If x is equal to b to the y power, that is exactly the same. That's the exact same statement as y is equal to log base b of x. The base here is the base here. The exponent, that's the variable by itself. That's what the log is equal to. And our x value is what we apply the log to. So here we go. Log base 4 of 64 is equal to 3. That's a fact. And the reason it's a fact is because our base here is 4. The thing that the logarithm is equal to is 3. And so that's our exponent. 4 to the third has to be equal to 64. And you could verify that 4 to the third is equal to 64. Because 4 to the third is 64, when we're evaluating this logarithm, what we'd say is the power that we would put on 4 in order to get 64, that's what the logarithm's asking, the power that we raise 4 to get 64, well, that power is 3. And therefore, that's what the logarithm is equal to. Okay, let's take a look at B. Log base 7 of the square root of 7 is 1/2. How would we say that? Well, we'd say, what power would we put on 7, or what exponent do we put on 7 to build the square root of 7? Well, of course, that power is 1/2, because our base of 7 raised to an exponent of 1/2 is equal to the square root of 7. The power of 7 that gives us the square root of 7 is 1/2, because 7 to the 1/2 is the square root of 7. So we've changed it from logarithmic form to exponential form. Let's do one more. Okay, if we write this in exponential form, I won't write this one out in words, but what would the exponential equivalent be? This is the same as saying the base of 6 raised to what power will give us 1 over 36? Well, 6 to the negative 2 power is equal to 136. And that should make sense because that's the same as 1 over 6 squared. So yeah, 6 to the negative 2nd power is equal to 136. Okay, let's go in the opposite direction now. Let's take these exponential equations and write them as logarithms. Here again, we're relying on this fact. If x is equal to b to the y, that's exactly the same as, see if you can complete this from memory now. That's the same as saying log with a base of b of x gives us y. Y is the power we put on b in order to make x. So let's take these statements, which you should all agree with, and turn them into logarithmic statements. 8 to the 0 power is equal to 1. That's true. And that means log base 8 of, what are we trying to build? We're trying to build the number 1. So what power do I put on 8 to build the number 1? 0 power. Log base 8 of 1 is 0. It's important to note that you cannot do these on your calculator. Your calculator can compute logarithms, but only certain logarithms, and we'll get to that in a little while. So these, you just need to be able to think of them in a logarithmic way. Okay, 6 to the 1/3 power is equal to the cube root of 6. That is certainly true. That's the definition of a 1/3 power. But what's the logarithmic statement there? That's saying log with a base of 6. And what are we trying to build? We're trying to build the cube root of 6. So what exponent do I put on my base of 6 to build the cube root of 6? Well, that's 1/3. Remember, the value of your logarithm is always an exponent, and our exponent here was 1/3. Okay, one more, and then I'm going to give you some for practice here. Our last one, 1/4 squared is equal to 1/16. That's certainly true. So what's the equivalent of that? Our base is 1/4, so log base 1/4. And what are we trying to build? We're trying to build 1/16. 1/4 to what power will give me 1/16? Well, I would have to square 1/4 to get 1/16, and therefore log base 1/4 of 1/16 is equal to 2. Okay? Hopefully you got the hang of that. If not, watch that again. Very important concept to understand. Let's keep going. Now, let's go a little bit further with that and introduce an unknown into some logarithmic statements. So log base x of 36 is equal to 2. What base would make this logarithm true? Well, we're going to solve these by rewriting them in exponential form. So log base x of 36 is equal to 2. Okay, here again is our fundamental relationship right here. Log base x of 36 is equal to 2. What's the equivalent exponential form? Our base is x. The thing that the log is equal to, 2, that's our exponent, and that has to equal 36, which is what we're trying to build. 36 is what's called our argument there. So x squared equals 36. All right, well, what does x have to be? Well, x could equal 6 or x could equal -6. But here's the thing. We're going to throw out -6 because the base on a logarithm always has to be positive. We cannot have a logarithm of a negative base, and we'll see why that is a little bit later. But right now, we'll just use that fact to say that anytime we solve for a base, we have to get a positive number. Any negatives have to get thrown out. Okay, number 2. Log base 7 of 343 is equal to y. Your calculator won't do that for you. We need to figure out what that is. So based on our basic relationship here, we can say that our base of 7 raised to an exponent of y, that has to give us 343. So what power would we raise 7 to get 343? Well, this number has been kind of contrived a little bit because it's true that 7 to the third power, 7 times 7 times 7 is 343, and therefore y has to equal 3. It must be the third power of 7 that gives us 343. Now, if we didn't know that, we would need a little bit more information, and we'll look at problems like that shortly. One more, log base 3 of z is equal to 4, so let's solve for z. Well, that's hard to think about in that form, but if we change the form, base of 3, 4 is our exponent, and that must equal what we're trying to build. Z is equal to 3 to the 4th. So 3 times 3 times 3 times 3, z must be 81, and we're done. Anytime we have a logarithmic equation, the first thing we do to try and solve it is we change it to exponential, because odds are we'll be able to solve the equivalent exponential equation. Okay, I want you to take a minute and see if you can solve these 3 practice problems. Pause the video and unpause when you're ready to see the solution. Okay, here we go. Log base x of 125 is equal to 3. Let's change that to exponential form. The base is x, our exponent is 3, and that'll build 125. So x to the third power is 125. Well, we could take the cube root of both sides, but x turns out to be 5. That's one you should recognize. Our second one, log base 9 of 3 is equal to y. Let's change that to exponential form. Our base is 9, our exponent of y, and that should give us 3. So 9 to the y power is equal to 3. But you probably recognize that the square root of 9 is equal to 3, and therefore you could conclude that y must be 1/2, because 9 to the 1/2 power, which is the same as saying the square root. is equal to 3. And our last one, log base 10 of z is equal to 6. So what is z? Well, let's change it to exponential. 10 with an exponent of 6 will give us z. And therefore, since 10 to the 6th is a million, z is equal to 1 million. Okay, now, just like when you see the square root of 7, we don't put an index on there, but you know that a square root deals with an index that is what? Well, you just understand that it's 2. Logarithms have something similar going on. If you see a logarithm written without a base on it, then we consider that to be the common logarithm. And a log with no base specified is the same as log with a base of 10. We treat these two equally. So let's take a look at a couple of example statements. The first one is log of 100. Log of 100 is 2 because 10 squared is 100. And therefore, we can, again, interpret that base to be 10. That's why it's true. Another example of that, log of 1/10 is equal to -1. Why? Because that unspecified base of 10 raised to the -1 power is 1/10. 10 to the -1 is 1/10. That's why it's true. And another one, log of 1 is 0. The reason is our unspecified base, which is 10, raised to the 0 power is 1, and you can verify that. Now, your calculator does compute common logs. So please take out your calculator now and try typing these in and verify that all three of these are true. If you type in log of 100, your calculator should say 2. If you type in log of 1/10, you might need some parentheses around that. You will find that log of 1/10 is -1. And if you type in log of 1 into your calculator, it should give you a result of 0 for the reasons that we've already described. So now that we're kind of familiar with how a logarithm behaves and what it actually means, there's just a bunch of logarithmic values that we want to evaluate. Okay, our first one, log base 6 of 36. What is log base 6 of 36? Well, now you know. What exponent would you put on 6 if you were trying to build 36? Well, we know that 6 squared is equal to 36. And because 6 to the second power is equal to 36, then the exponent I'd put on 6 to build 36 is 2. Log base 5 of 1/5. What power am I going to put on 5 if I want to build the number 1/5? Well, 1/5 is the reciprocal of 5, and so the exponent I'd put on there is -1, and therefore 5 to the -1 power gives me 1/5. Okay, log base 9 of 3. What power do we raise 9 to get 3? We already saw this. We know that 9 to the 1/2 power, or square root of 9, is equal to 3, and therefore log base 9 of 3 is 1/2. Log of 100. Now we saw this just a minute ago, but I want you to start thinking about this now so that you don't need a calculator. What power do I raise our base to build 100? Well, our base is 10. Since there's nothing specified, we can assume it to be 10. What power will I put on 10 to build 100? It's going to be equal to 2. Your calculator would verify that one. Log of 1. What power am I putting on my base to build 1? Well, the base is 10. So what power do I put on 10 to build 1? Well, because 10 to the 0 gives us 1, our exponent must be 0. In our next lesson, we're going to deal with some properties of logarithms, and that's going to turn out to be an important property. Okay, here's a tricky one, log of 0.001. You could type this one into your calculator. Your calculator will evaluate anything that's a common log, or base 10, but we don't need our calculator to do that. The question is really saying this. That's the same as log of 1 over 1,000, right? 1,000th is 1,000th. And so really what this is saying is our base of 10 raised to what power will give us 1 over 1,000? Well, 1,000 is 10 to the third, but we want the reciprocal of that, so our exponent must be -3. And therefore log of 0.001 is -3. You can verify that by typing it into your calculator. Okay, I want you to type this one into your calculator. Take a minute and do this one. Type in log of -10. Okay, well if you type in log of -10 into calculator, you will get an error. Or your calculator might say domain error. And here's the reason for that. The domain of the log function, we can only plug in positive numbers. For logarithms, the base has to be positive and the argument has to be positive. We'll see why that is in a minute, but at this point we're going to note an important fact about logarithms. The domain of a logarithmic function is from 0 to infinity. We'll see why that is in just a minute. Okay, log of 357. You can type that one right into your calculator. Go ahead and do that. If you type that into your calculator, you need to keep a lot of decimals when you're dealing with logarithms. You should get 2.5527. Now, how can you check to see if that's actually true? Well, let's check it by doing this. Take 10, that's our base, and raise it to the 2.5527 power. 10 raised to the 2.557 power. Now 10 squared would be 100, that's too small. 10 to the third would be 1,000, that's too big, so this should be right. And if you do that, you will get about 357. A little rounding error might leave you a little off, but it should be pretty close. And the last one, log of 8.5. Type that one in your calculator. Well, that one turns out to be 0.9294. And it should make sense that that's less than 1 because we know that 10 to the first power would give us 10. We're trying to figure out 10 to some power that will give us 8.5. It's got to be a little bit smaller than 1, and it is. So you can check that by taking 10 to the 0.9294 power, and you should get about 8.5. Okay, and now we're solving some logarithmic equations based on what we know. But here's the key. I want you to really get comfortable with this idea. Anytime we're stuck on an equation, whether it's logarithmic or exponential, we're going to see some of each here. It's always best to switch from one form of the equation to the other. We can always switch between exponential and logarithmic. If one of them is not solvable, the other one probably is. If b to the y is equal to x, that is equivalent to saying log with a base of b of x is equal to y. So let's go after these. Let's solve log of x is equal to 6. You can't type that into your calculator because we don't know what x is, but we can change forms. Our base here, 10, exponent, 6, equals x. So x is 10 to the 6. Here it is again. We saw that earlier. X is 1 million. Solved. Our second one, log of z is negative 0.5. We can't type that into your calculator, but you can change the form. Our base of 10 raised to the negative 0.5 power has to give us z. 10 to the negative 0.5 power, that you can type into your calculator, and you should get a z value of 0.316. Okay, the bottom one, 10 to what power gives you 1,000? Well, you can probably solve this one without too much trouble, but let's change that to logarithmic form. That's saying log with a base of 10 of 1,000 should be our exponent n, and as we saw earlier, the log of 1,000 is of course 3. 10 to the third is 1,000. That's an easy one. What power of 10 gives you 0.01? Well, we can switch that to logarithmic and say log with a base of 10, we don't even have to write it, of 0.01 is equal to y. So you can type that in your calculator, log of 0.01, and you will get y equals negative 2. Makes sense? 10 to the negative second power is 1 over 100, or 0.01. Now our third one, this is a bona fide tricky problem. 68,327 equals 10 to the 3n plus 4.7. Before today, we would stare at that and have no idea where to begin, but now we know. We can convert this to logarithmic form, and we can say log with a base of 10 of 68,327, and that's what we're trying to build, has to be equal to our exponent of 3n plus 4.7. Now, we don't need that base of 10 on there. We can simply say log of 68,327 is equal to 3n plus 4.7. And the good news is this is a common log, so you can type that right into your calculator. Log of 68,327 is 4.8346. That has to equal 3n plus 4.7. Well, now it's a piece of cake. Let's subtract 4.7. So 0.1346 is equal to 3n, and if we divide by 3, we'll have solved for n. And n is 0.0449. And we've solved what would have been a pretty horrible equation. Logarithms make it easy. Okay, so we've accomplished most of our goals already. You can switch between exponential and logarithmic form, and you can solve logarithmic equations, at least some of them. So let's take a look at some of the properties of logarithms now and the way their graph behaves. First of all, let's graph the function f of x equals 2 to the x. We've seen this before. That's an exponential function with base 2. Our a value in front of there is 1. And so based on that exponential function, a being 1, we know that we're going to cross at 0, 1. And since our base value here is 2, after all, that is of the form ab to the x. And so then every time we move to the right, we can double our previous value. 1 becomes 2, becomes 4, becomes 8, becomes 16, and all of a sudden we're right off the graph already. And of course, if we follow that back, we're just going to hug the negative x-axis. There's the graph of f of x. So what will the graph of log base 2 of x look like? This is important. Let's go back to our exponential function, f of x is equal to 2 to the x. Let's review our three-step process for finding the inverse. We already know that it's going to have an inverse because that graph passes the horizontal line test. It's 1 to 1. Okay, remember, we started out by calling this thing y equals 2 to the x, and we want to switch x and y around. So this becomes x equals 2 to the y. Then, hopefully you remember, we're going to solve for y. X equals 2 to the y, solve for y. Well, wait a minute here. This is the very problem that we started out the day with. If we're trying to solve for something that's in the exponent, it's tough. We can't do it. So we rewrite this in logarithmic form. To solve for y means we switch it to y equals log base 2 of x. There it is. We solved for y. And that means that that is our inverse function. F inverse of our original function 2 to the x is log base 2 of x. That means the inverse of a function that is an exponential function is the logarithmic function. The inverse of an exponential function is the logarithmic function with that same base. And that's true whether it's exponential growth or decay. B to the x has an inverse of log base b of x. So what does that mean about our graph? It means that the second function, g of x, that we're asked to graph here also happens to be the inverse of our first function. And what does that mean about its graph over here? It means that we can reverse all these points that we know and reflect them over the line y equals x. So this point here, 0, 1, becomes 1, 0. This point 1, 2 becomes 2, 1. This point, which was 2, 4, becomes 4, 2. This point up here, which was 3, 8, is going to become 8, 3. And so that is the graph of g of x, which is log base 2 of x. Now notice, what's the domain of this function? The domain goes back to 0 but never touches it, and it goes off to infinity. So our domain is from 0 to infinity. That should make sense. We said earlier, when I asked you to evaluate log of -10 on your calculator and you got an error message, that's why we can't plug negative numbers into a logarithmic function. It's not in the domain. The domain is only positive numbers. So we can't go back here into negative territory to evaluate a logarithm because they only extend through the positive numbers. So you won't be surprised at all to know that this logarithmic function that we just graphed, that's one of our base functions, and we'll define that in a minute. But we can apply all our normal transformations to it. So what happens if we take log base 2 of x and add 3 just to the x? That's an inside transformation. That's going to move it up, down, left, or right. Now that's going to move it left 3. And then we're going to make the whole thing negative, which will flip it over. So if we take our original logarithmic function and move it left 3, I'm going to do that in a dashed line. All these points get moved 3 units to the left. And that dashed line is our logarithmic base 2 function moved to the left 3. And then we'll flip that over. So the point on the x-axis, that's going to stay right there. This point that was 1 above is going to get flipped down. This point that was 2 above is going to get flipped down. And so if we flip it over, we get that dark function right there. That is the graph of negative log base 2 of x plus 3. Now before we summarize these this new base function that we have, let's take a look at one more thing. Let's graph f of x is equal to 1/2 to the x power. Here again, that's of the form ab to the x. That is exponential. There's a leading coefficient of 1 out there, and so that means that a is equal to 1 and b is equal to 1/2. So that's going to be an exponential decay graph, right? Intercept of 1, and every time we move to the right, we're going to have half of what we had before. So that's going to decay down to 0. But if we move to the left, everything will double. 4, 8, and so on. So there's the graph of f of x equals 1/2 to the x power. Then what will g of x look like? Hey, we know. G of x is going to be, since it's log base 1/2, that is the inverse of our original function. So to figure out what this looks like, again, we can just flip all the points over the line y equals x. So the point 0, 1 becomes 1, 0. We had the point -1, 2, that becomes 2, -1. We had this point back here at -2, 4. It's going to go to 4, -2. -3 up 8 means we're going to go to the right 8 and down 3. And if we graph that inverse function, it's going to cling just greater than the y-axis in the same way that the original function stayed just greater than the x-axis. And there it is. So we have 2 more base functions to add to our list, giving us a total of 9. And that's all of them. That's the last of the 9 base functions we're going to learn in this class. Let's summarize those 9 base functions. Okay, real quickly, our first 5, which you should know real easily by now. We started out with x squared. That is a basic old parabola with vertex at the origin. X cubed function climbs a little bit faster than the x squared function, but it also twists and goes downward into the third quadrant. Absolute value of x, that is, of course, our v function. And then we graphed the square root of x. That has a domain of 0 to infinity. That's half of a parabola, otherwise it would fail the vertical line test. And the cube root of x is the reflection of the cube of x, and also its inverse. Now all 5 of those have the property that they pass through the point 1, 1, as well as the origin. And then earlier in this section, you learned number 6 and 7 in terms of our base function. An exponential function, ab to the x, where b is bigger than 1. We have exponential growth, and that one, of course, takes off and looks like that. But if b is less than 1 and still greater than 0, then we have exponential decay, and that function comes down and never quite touched but gets infinitely close to 0. So that was base function number 6 and 7. And as we just saw now, we can add numbers 8 and 9 to that. Our eighth one, if our function is equal to log with a base b of x, where b is greater than 1, then we get the reflection of this over the line y equals x. And if we reflect that over the line y equals x, we get its mirror image, which is the logarithmic function with base greater than 1. And our ninth function is the logarithmic function where b is between 0 and 1. And that is the reflection of an exponential decay function over the line y equals x. So instead of going down and hugging the positive x-axis, it hugs the positive y-axis, and it will look like that as we just saw in our previous example. And with any of these, all of the transformations we learned apply. We can shift them up, down, left, right, or we can flip them over. And so these new 4 plus our original 5 give us all 9 of our base functions. Make sure that you know those. Those are excellent stuff to put in your note sheet for a final exam. Okay, let's wrap this up by looking at one small applications. Logarithms are used a lot in the sciences. They're used in chemistry for calculating pH value. They're used in electronics and sound for measuring decibel level. And they're used in one version of the Richter scale, which measures earthquake intensity. Nice simple little formula here. The value on the Richter scale, or intensity of an earthquake, is given by a log of A over P, where A is the amplitude of ground motion. That is to say, in micrometers, that's 10 to the negative 6 meters. That's how far up and down the ground shakes during an earthquake. That's what a seismometer measures. And P is the period. That is to say, the time of a complete oscillation of the Earth's surface. Now, that's happening pretty fast during an earthquake. So let's look at an example. We can calculate what the Richter scale measurement of an earthquake is if it's got an amplitude, that is to say an A value of 5,000 micrometers. That's about a half a centimeter, a little bit less than the thickness of a typical pencil. So that's not very much vibration on the surface of the Earth. And a period of 0.2 seconds. So that would mean the Earth is shaking 5 times or making 5 oscillations in a whole second. Well, this is pretty straightforward. Then our R value, our Richter scale value, is going to be log of our amplitude in micrometers, 5,000, divided by P, our period of 0.2. That's equivalent to saying log of 5,000 divided by 0.2 is 25,000. You can type that directly into your calculator and you get a Richter scale measurement of 4.4. And there will be other applications like that in your WebAssign work today. Okay, let's summarize what we've done today, and I'm going to work backwards. The most recent thing that we worked with were the graph of the functions. You need to be familiar with these four basic cases. We know from our earlier lessons that exponential growth takes off. Well, the reflection of exponential growth, that is a logarithm with a positive base bigger than 1. And so a logarithmic function has the same shape as exponential growth, but it's flipped over our symmetry line y equals x, or the identity function. Whereas if you flip exponential decay over the line y equals x, that gives you the other type of logarithmic graph where the base of your logarithm is less than 1. But in both cases, the second thing that I want you to recognize, that for both this graph and this one, look at the domain. Both of them start at 0 and go to the right. Even this one starts at 0 and goes to the right. So for all logarithmic functions, the domain is from 0 to infinity. And that's why when we evaluate the logarithm of a number, it has to be a positive number that we put in there. Otherwise, our calculator will give us an error. The second thing that is very important for you to remember is that when you see a logarithm with no base specified, you can treat that as base 10. And these are the only logarithms so far that your calculator can handle. If we've got to base anything other than 10, your calculator probably won't do that. But that's okay. We're going to work that out in our next section. And the most important fact of the day is this one right here: the relationship between a logarithmic statement and its exponential form. If x is equal to b to the y power, then it has to be true that our exponent y is found by taking log base b of that x value. This you should tattoo on your arm. This is an extremely important fact. All of our logarithm work is based on that statement. Okay, that's it. Go ahead and do the WebAssign for this section. As always, reach out if you have questions. And we're going to continue to build on these ideas in the next section.